So lesson 3 for forces, friction. Friction is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. So although a surface may appear very smooth, if you zoom in on the atomic scale, Grayson, it's not. So here is my zoom in picture. This is a box or a block sliding along a table or a counter, but if you zoom in, it's jagged and they interlock with each other. Friction's a very complicated force. Friction resists sliding, and so as such, Raffi, it can resist motion, such as for sliding objects when you're trying to slide something across the floor, but it can also create motion when you walk or with your car tires pushing your car forwards. Example 1, I wrote here, draw the direction of friction in each case. Okay, if the motion of the block is to the right, what direction is friction? So we would add a little, and my abbreviation for friction is FFR. FFR. B, a car speeding up. This one is very counterintuitive. In fact, I've even had to correct physics teachers over the years where they have told me that for a car, when you hit the gas, don't write this down. They'll say, oh, friction is that way. That's wrong. I'm going to try and convince you of it. Rachel, if you follow the wheels all the way around, right here, what direction is the wheel pushing? Right here, what direction, folks, is the wheel pushing? Backwards. Its motion is backwards. And since friction resists motion, what direction is friction? This is a very counterintuitive one to realize that friction, when you hit the gas, is what's pushing your car forwards. It's a Newton's third law thing. The tire applies a force backwards against the pavement. Newton's third kicks in, forces come in pairs. Friction is what pushes the car forwards. What about for a car slowing down? Now, when you slow down, now the tires exert a force in that direction. So which way is friction when you slow down? Backwards. What if you demand a bigger force of friction than it's capable of giving? Well, then you have unbalanced forces. Newton's first kicks in. You're going to continue to accelerate forwards, and that's a car accident. Okay? There's bad driving. There's bad physics. I'll hopefully talk you out of both during this lesson. The amount of friction depends on two things. The first thing, Naomi, it depends on is the type of surfaces that are in contact. How smooth they are or how jagged they are. And we represent jaggedness by the coefficient of friction. Symbol, a Greek letter mu. So mu, the coefficient of friction, talks about how sticky an object is. If mu is large, there's lots of friction. If mu is small, there's little. So steel on ice, which has very little friction, has a mu of about 0.01. Rubber on concrete has a mu of about 0.075. Wet tires have a mu of approximately 0.35. When it's raining, your coefficient of friction goes down by about 50%. What that means, Mark, is that it has nothing to do with your skill as a driver. You cannot demand more of friction than it's capable of doing. You need to slow down or book or budget more time to stop when it's raining. And I always see, stereotypically males who are stupid. They, oh, I'm a good driver, I can stop. Has nothing to do with your skill level. It's the laws of the universe and physics. Slow down. Give yourself more time to stop. Snow, even lower. Slow down. So Grayson, how big the force of friction is depends on mu, how sticky the objects are. And it depends on the forces pushing surfaces together. Last year, that was almost always gravity. This year, that will almost always not be the case. The force that pushes surfaces together is the normal force. And this gave us our equation from last year. This is the second equation in this unit on your yellow sheet. The first one was F net equals ma. The second one is friction equals mu times the normal force times how hard the ground has to push up against me. Consider the block below, which is being pulled by student number 1 across a rough surface at constant speed. You know what? Let's imagine the benches in the gym, the ones that slide at the back of the gym. Most of you have pushed those around at least once. So you're sliding it along the gym floor at a constant speed. One of your meathead friends comes along and decides it's going to be funny if they jump up and land on the bench while you're pushing it. What will happen? Okay. So here's what the question asks. Right now, we're pushing at a constant speed. Suddenly, student number 2 pushes down on the block with a force F. Let's say they've just decided to sit on it. Instead of pushing down, they've jumped on it. What happens, first of all, to the weight of the bench? What's weight another name for? By the way, it's not another name for mass because weight is measured in newtons and mass is measured in kilograms, but you're close. I'm sorry, what? I didn't hear. No, it's not the normal force. Jordan. Okay, weight is another name for mg. When this student pushes down on the bench, does the mass of the bench change? So does the weight of the bench change? And this is why we don't describe friction in terms of mg. You know what? Let's say equals the same, unchanged. B, what happens to the normal force? So right now, if you look at this table in front of me, the normal force is equal to mg. I'm going to push down on this table. Did the mass of the table change? Say no. What happened to the normal force? Why did it increase? Because now not only does the normal force have to cancel out mg, Newton's first, what else must it cancel out? And if it wasn't, this would either sink into the ground or fly into the air. That's my proof. The fact that it's not, I know all the vertical forces must be balanced. So what happens to the normal force in this situation if we push down while someone is pushing the bench? Increase, decrease, or stays the same? Increase. My abbreviation for, so first of all, Fn increases. My abbreviation for increase is arrow pointing up. My abbreviation for decrease is arrow pointing down. Clue in, I tend to abbreviate. C. So what happens to the force of friction? Well, if friction is that, and if the normal force gets bigger, what happens to the force of friction? Right? And then the last thing it says, so we're answering the questions. What happens to the weight? Check. What happens to the normal force? Check. What happens to friction? Check. Oh, what happens to the motion of the block? I can be more specific than Valoria because of what I underlined in the question. Valoria said it gets tougher to push. I can be more specific than that. You know what happens to the motion of the block? I can be more specific than that. It's going to decelerate and it has to come to a rest. Has to. Why? We'll draw the free body diagram in a second. But slows, and stops. You see, Mickey, if we're at a constant speed, then right now, these two were identical. If friction got bigger, now I have a net force pointing to the left, which means I'm going to decelerate to the left. But, and this goes back to my earlier comment with Rafi about the question you asked from the homework, friction is only as big as it needs to be. Once it stops, friction is not going to keep it moving somehow magically to the left. Friction, it's going to stop, and then we're good. Is that okay? It says explain your answer. We just did over there. So in our box, we calculate friction as follows. Friction is mu times the normal force. If you want to see me freak this year, tell me that friction equals mu mg. It does not, and I've never, ever, ever, ever said that. It so happens last year, Josh, in Physics 11, because you guys were so ignorant, there, friction almost always equaled mu times the normal force, but the normal force was almost always mg, and so you may have noticed in Physics 11, friction always ended up being mu mg. It will not be in Physics 12, and I will snap if I hear somebody say, oh, force of friction, that's mu mg. No, it's mu times the normal force. Mu times what? Mu times what? Okay. What are the units for the coefficient of friction? What's mu measured in? Nothing. It's a unitless measurement. It's a ratio. It's a ratio. The closer it is to 1, the stickier it is. In fact, you can have mu's bigger than 1. Dragster tires have a mu bigger than 1. Which force pushes a dragster forwards? Friction. That's why you would want your dragster tires to be as sticky as possible, because the stickier they are, the bigger the friction force, the better the acceleration. That's also, if you watch dragsters, the reason they do the smoke show at the beginning, the reason they spin out is not to impress the crowd. What are they doing to the tires when they spin it out? They're heating them up, and when rubber gets heated, what happens to it? Stickier, less sticky, or stays the same? Sticky. It's all physics. Okay? They've thought it through. Example 3. And since this one has 4 choices, we're going to do our, once again, vote. A student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best force diagram for the cart after the student has released it? A, B, C, or D. Let me give you an illustration here. Pause. Which of those diagrams best represents the free body or force diagram after the student has released the cart? Who says, it's got to be A, Mr. Dueck? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Mickey, don't think I didn't notice. You look around and then vote. 15. Who says it's got to be B, Mr. Dueck, because forces come in pairs? 1, 2, 3. Who says, Mr. Dueck, it's got to be C because no one's touching it, so there are no forces horizontally? And by the way, I'm telling you possible, plausible explanations. No one. Who says, Dueck, obviously it's D because the cart's moving forward, so there must be a force forwards? No one. 18 of you votes, 10 of you are cowards. Joseph, what? Is it B? Convince me. So forces come in pairs. Now here's the problem, Joseph. I sucked you in with that comment. Forces do come in pairs, but that second force, the one pointing forward, I should have drawn that on the ground because that's where it's acting. And so even though forces come in pairs, if we're only drawing a free body diagram, the pair won't show up. We know that the pair is out there acting on whatever else that our object is touching, but it's not going to show up on here. So sorry, I have to say to you. By the way, if that was the free body diagram, if B was correct, what could you tell me about the motion of the cart? Sorry? It could either be not moving because the forces are balanced, or constant speed, straight line, steady speed because the forces are balanced. So it could be outer space like a spacecraft just coasting along, or an air hockey puck on an air hockey table just coasting along, or it could be at rest. But I don't think the shopping cart goes forever and ever in a straight line at a constant speed. So hopefully I've given you a good reason. You with me, Joseph? Hopefully I've given you two different ways to think about why that can't be the case. Whoever's whistling can stop. Thank you. So, A is right. How the heck can A be right? If the cart is moving to the right, how can the net force be to the left? Okay, this is the same as last class. I asked you the same question for the baseball on its way up. We drew the free body diagram and we noticed that both gravity and air resistance were pointing down, and Rachel asked, well, how can that be? Velocity and acceleration don't necessarily have to be in the same direction. Eventually, they'll probably end up that way. So A is correct. What are the forces acting on this cart? Get the obvious one. This is gravity. Is the cart sinking into the ground like quicksand? Is it flying into the air like Superman? So vertically, the forces must be in balance. The ground must be pushing it up vertically. Here's my normal force. What is that force pointing to the left? Friction, which means the cart is going to slow down, it's going to slow down, it's going to slow down, it's going to decelerate, and eventually it's going to come to rest. Once it comes to rest, I said friction acts in the opposite direction of motion. Once there is no motion, how big is friction? Then my free body diagram would be C. That would be the correct free body diagram. For each of the blocks below, write a vertical force equation, write a horizontal force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? I'm going to call this 1, I'm going to call this 2. And I'm going to say to you, I like example 2, I like example 2, I like example 2, example 2 is the next question. But let's do number 1 first. Okay? Mac, what does A want me to do? You know what I should do first? You know what this is a job for? This is a job for a free body diagram. Although, you know what? Since they gave me a lovely picture, rather than redraw everything, I'm just going to label the forces right on this box, which technically is not a free body diagram. Rachel, technically a free body diagram is when you represent the mass as a dot. I'm going to be a bit lazy, and I'm going to put the forces right on here. What are the forces acting on this box? Get the obvious one. Okay. Is this box sinking into the ground like quicksand? Is it flying into the air like Superman? So there must be a force, and it's got to be the same size as gravity. What else? Well, we have this 20 newtons. That's the applied force someone is pulling. I heard someone say one more. What? Friction. Now, how do you know that there's friction? Usually, you'll see a mu somewhere in the diagram. Now, if you see mu equals 0, that's my shorthand way of saying pretend you're on ice, no friction. But there's a mu. Which way would friction be acting? What direction? Which way is this box going to be moving? So which way will friction be pushing? Which way, what direction is this box accelerating? To the right, so who's winning? Okay. Oh, first of all, A says write a vertical force equation. Fair enough. I think mg equals Fn. Vertically, normal force and mg cancel each other out. Put your pencils down. Look up. By the way, what I really did was this. I went winner minus loser equals ma. Don't write that down. Except vertically, what's the acceleration? Is this box sinking into the ground like quicksand? Is it lifting into the air like Superman? So what's the vertical acceleration then? 0. So really I would have this, but then how would I get the Fn by itself? Rob, how would I get the Fn by itself? And that's how I said, pick your pens up, we got right to there. If you can do that in one step, I'm good with that. There's my vertical force equation. B. Nate, what does B want me to find? Well, friction equals what times what? What's our equation of the day? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. And that is always going to be our approach. There will be very, 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 very few situations where we'll know the normal force. In fact, I don't have a formula to calculate it. But I'm telling you, Mark, in a good free body diagram, every time you should be able to look, and figure out what the normal force is. And I do that stupid rant on purpose to jog your memory so that you know you have to go looking for the normal force. In this case, I know the normal force is the same size as which force? And that's why, Joseph, last year, that worked for friction pretty much every time, because we kept it simple last year. What's mu? I don't know. What's mu with you? No, what's mu in this question?
0.12.
The jokes only get worse, people. Just telling you. What's the mass? 10. G is 9.8. Not negative. I've decided in this case, based on this equation, to let down be positive. How big? You know what? I should be able to do this in my head. Let me see. 10 times 9.8 is 98. 98 times 0.12 is going to be 9.8 plus 1.96. 10.9? No, 11.76? Double check me. Yeah? Okay, you know what? Since I'm going to use this later, I'm going to write it in its full glory. But then since this is also an answer, I'll go to 3 sig figs and I'll say 11.8 newtons. You guys should be a little impressed. I did some good math in my head there. I didn't even use my usual trick of memorizing the answer. I actually did that one. C, I've scrolled down. What did C want me to find, Zach, in the back? Oh, I was going because there's several. Horizontal force equation. Zach, look at my horizontal. Who's winning? Which way is this thing accelerating? So you're right, but which direction is this thing accelerating, if it is at all? So who's winning? To the right. Which force is that applied? So anything that's pointing to the right will be winner plus in my equation. Anything that's pointing to the left will be loser minus in my equation. So Shaq, the equation, I don't mean to look at you when I said loser. It's going to be winner minus loser equals MA. Mickey, what does part D want me to find? By the way, part C, Zach, you just said write an equation, right? Zach? Yeah. Just, okay, done. Sorry? How would I get the A by itself? Will the mass cancel if I do that? Okay, just pointing that out. So you're saying A is going to be the applied force minus friction divided by the mass. Stop. Look. What if we were dealing with a heavier object? Looking at this equation, can you predict if the object was heavier, what would happen to the acceleration? Bigger, smaller, or stays the same? Now this seems really obvious, but that's why it's tougher to move heavier objects. There's the physics. And the heavier it is. Oh, in fact, there could come a point where this mass got so big that friction would be so big that it's bigger than the applied force. That's when you say, I need some help here. Right? That's the physics of what's going on. At least once in your life, you're going to be asked to move furniture for a friend for free pizza. You'll appreciate this physics a bit more when you're doing some of that. Believe me. How big was the applied force? I've scrolled down. What was it? 11, 20, what? 20, okay. Minus Friction was 11.76 divided by 10. Oh, I can do this in my head. 20 take away 11 is 9, take away 0.7 is 8.3, take away 0.0 is 8.24. 0.824? Double check me. It's dividing by 10. Really, that one wasn't that impressive. Part 2, I like part 2, I like part 2, I like part 2. Part 2 is a nice question. Yeah. Quick click of money. Okay. It wants us to find all the same stuff. Rob, you know what this is a job for? Except, you know what? Instead of redrawing everything, is it okay if I just label the picture that they gave me? All right? And I'm totally good with that. The only time I'm not good with that on a test is if I actually say, draw me the free body diagram for marks, and I leave space. I don't want you to label my original diagram. I'm going to be fussy and say, put the free body diagram in this space. And it probably means it's a tricky free body diagram. Be careful. Just Physics 12. Okay, what are the forces acting on this box, Rob? Get the obvious one. What else? There is one more that they gave me. Can you see it? Another vertical force. What? 15 newtons. What direction? Down. Is this box sinking into the ground like quicksand? Is it flying into the air like Superman? Okay, look up. All of you look up. Yes, you too, Naomi, look up. Look up. Look up. This would be wrong. Can you tell me why drawing the normal force the same size as mg is wrong? The normal force not only has to cancel out mg, what else does it have to cancel out? So if I gave you this hint, as a free body diagram to draw, absolutely I would take marks off if you got sloppy, because most of the time last year, mg and the normal force were the same size. Brendan, if you drew the normal force the same size as mg, I'd be taking marks off. In fact, I'm going to exaggerate it a little bit. Well, you know what? The normal force should be as long as both those vertical arrows put together, which in my diagram is about like that. Give or take. What else? I have a 20 Newton applied force. Cool. What else? Friction, because the question has a mu. What's mu? I don't know. What's mu with you? Oh, the 0.12, right? Mickey hasn't heard my lame jokes yet. Eventually, she'll stop laughing. Oh, that was Mark laughing? That little giggle was Mark? Okay. Mark's a giggler. I didn't know that. Tee. Okay. Boy, talk about accidentally emotionally scarring him for life. Could be worse. I could have made a joke about your height. Never mind. Yeah. Okay, we're back. Hey, you could beat me in one-on-one, so shut up, Mr. Dueck, right? Pardon me? Oh, battle of wits with an unarmed man, right? Here we go. Mark, my friend, what does part A want me to do? Can you write for me, looking at this free body diagram, can you write for me a vertical force equation? I'm going to give you a hint. Look up. Is this sinking into the ground like quicksand? Is it flying into the like Superman? So I skipped the step of saying winner minus loser equals 0. I'm saying, you know what? Everything up has to cancel out everything. So what's down? Ah, do you see? And this is why if you ever say to me for the rest of this year, oh, friction is mu mg, I'll freak. Friction is mu times the normal force. I don't know the normal force, but look. I know another thing the same size as the normal force, mg plus 15. which leads me to part B. Part B says, find friction. Josh, friction is what times what? Yeah. Careful, is normal force mg this time? Nope. So it's going to be 0.12 times mg plus 15. Friction is going to be 0.12 times 10 times 9.8 plus 15. Do that one in your head, Dueck. Oh, maybe. 10 times 9.8 is 98, plus 15 is 108, plus 3 is going to be 113. 0.12 times 113, ooh, this one's going to be yucky. It's going to be 11.3 plus 0.22, 11.52 something? No, I'm off. It's got to be bigger than that, Mr. Dueck. You forgot to carry a 1. What is it? 13.56. I should have had that. There's the longer, non-rounded off version, but now Valoria is my final answer for part B. I'll go to 3 sig figs, which is 13.6 newtons. I'll put a little box around it for the marker, but for the remainder, I'm going to use the 13.56. By the way, when we go through our Unit 1 test, some of you are rounding off way too early at the beginning. Don't do that. Always use your longer versions for further calculations. Jenny, what's C asking me to find, kiddo? Oh, if this thing is accelerating, what direction is it accelerating, Jenny? Yeah, by the way, can it be accelerating to the left? Friction cannot create motion on its own. It's not going to magically... See, put your pencils down, look up for a second. Let me pause this. So based on that, Jenny, looking at the free body diagram that we have up there, who's winning? Yep. Who's losing? Why don't I put mg or Fn in this equation? Because they're vertical and they don't go into a horizontal. Worth emphasizing from last unit too, but Naomi, it still matters. All your forces that are in a straight line go in the same equation. Don't be putting forces that aren't in that straight line. So, applied minus friction equals ma. Is that okay, Jenny? Okay. Anita, what's part D asking me to find, kiddo? How would I get the A by itself in my equation? Oh, and usually once you get the equation, usually after that, the arithmetic is fairly plug and chug-ish. But it's getting the equation, which is why I'm spending, and this is a job for a free body diagram, I'm emphasizing that. So it's going to be applied minus friction divided by the mass. It's going to be 20 minus 13.56 divided by 10. I should be able to do this one in my head. 20 take away 13 is 7, take away 0.5 is 6.5, take away 0.06 is 6.44. 0.644? Double check me. Yeah? I'm still choked I couldn't come up with that 13.56. Double check units and everything. Yep. Look like a bunny, I guess. Some of you need to pace yourselves a bit better during lunchtime or drink less. Next page. There can be friction on an object even when it's at rest. We call this static friction. In fact, Mickey, I have to go to my proper physics versus bad physics. Mickey, you with me? There technically are 2 types of friction. There's friction while moving, and there's friction while standing still. We're going to pretend that there's only one type of friction to make the physics easy, Brendan. but I have to point out as a nerd. So here's our example 6, and once again, since there's A, B, C, D, we're going to vote. It says this. If we pull on a desk with a force of 2 newtons, and the desk does not move, then which of the following is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there's no static friction. What are you talking about, Dueck? Once again, we're going to vote. So if I pull on a desk with a force of 2 newtons and the desk does not move, which of the following is true? Who says, Mr. Dueck, it's not moving, so A has to be right because friction's got to be bigger than your pull? Who says A? 1, 2. 2. Who says, Dueck, it's got to be B? Ooh. Who says C? Why must C be wrong? If static friction was less than 2 newtons, what must happen according to Newton's first law? It would have to be accelerating. And not just moving, accelerating. And that's silly. Okay. Now, to those of you that voted A, if static friction was bigger than my pull, would I have balanced forces? So, by Newton's first, I'm telling you, Newton's first is a powerful law. What must happen? If static friction was bigger, what must happen? It would have to be accelerating. It's not, so it has to be B. So, going back to my desk. So it says, explain your answer using principles of physics. I think we reasoned it with Newton's first, right? We said it has to be equal because the forces must be balanced. That's what Newton's first law says. So here typed out is the same rant that I just went on. It says static friction is thus a force that varies from 0 when we're not pushing on the object up to a maximum value. And as soon as we push harder than that maximum value, the object must move, accelerate. Okay? Static friction is only as big as it needs to be, though. And so often we use as a symbol for static an S, and we say friction is mu static times the maximum normal force that it's capable of exerting and creating, and that's your maximum static friction. If an object is sliding, we call the friction kinetic, moving. Kinetic friction is mu k times the normal force, but we are going to pretend that those are one and the same. Football players. In football, coaches often say low man wins. Or basketball players, how do you box out Shaquille O'Neal? Okay? Using principle, that's how do you defend, how do you box out a guy that's bigger and stronger than you? Or in football, why does low man win? Using principles of physics and a free body diagram. Explain why this is the case. So, Shaq, I'm sure your coaches have told you, you've heard the expression low man, get down low. This is why. They may not know the actual physics why, because coaches don't necessarily get into the physics of it. It's all passed down. But here is why they are right in that. Okay? Come on. Okay. What's your homework? Number 1. 2. 3 is good. 4 is good. 5 is good. 4 and 5 are so tough that they're they're so easy that they're tough. Almost inevitably, I get asked about 4 and 5 the next day. I probably will. And then when I set it up, oh, really? And I love questions like that because I'm really trying to teach you, Mark, a first principles approach to physics. Your hint for 4 and 5 is a good free body diagram. Number 6, I'm going to circle and put a star next to. This is an example of a algebraic proof. See if you can prove that when we're talking about a car, that is the equation for stopping distance. Now, what you're actually going to have to do is do a good free body diagram, find an expression for the acceleration, and then I think if you plug that a into vf squared equals vi squared plus 2ad, you should be able to actually get an expression, get the d by itself. Try it. I'm not going to worry about 7 because number 7 is talking about 2 different types of friction, and I've told you while that's true, I'm not going to be assessing you that way this year. 8 is a bit long and tricky, but okay. 10 is good. We'll pause there.